Rachel.
Okay, thanks very much. So I'm currently a postdoc based at the ITC, but until a few months ago, I was a PhD student at the University of Edinburgh. So this work's done in collaboration with my supervisor there, Philip Best, and also with Chris Hayward and Danielle Anglas-Alcazar, both at the CCA. So I start by talking about what we can learn from observations, in particular, what we know about the global properties of galaxies, as well as what we can see at high spatial resolution. And then I'll talk about some work I've been doing to use the FIRE2 simulations to interpret these observations. So through my PhD, I was using data from HISLS, which is the High Redshift Emission Line Survey, to map star formation at multiple redshifts. So we do this using narrowbands, so picking out star-forming H-alpha emitting galaxies within very well-defined redshift slices. So we had thousands of galaxies at redshift 0.8, 1.5, and 2.2. And from this survey and from many others using different wavelengths, we've kind of realized that the star formation rate density of the universe, shown down here, increases to a peak back around redshift 2 when the universe was around 20% of its current age. And these large samples were really good for characterizing the population in terms of luminosity functions, probing dark matter halo environments via clustering, for example. But the galaxies aren't spatially resolved, so we can't see where star formation is happening within the galaxies. One key goal is to understand how stellar mass is assembling, not just in a global sense, but also within individual galaxies. So to address this, we've recently targeted a subset of these H-alpha selected galaxies at much higher spatial resolution with a number of different instruments. So we called this campaign SHISLS. And this is data at around 0.15 arc-second resolution in the UV and rest frame optical from HST, mapping H-alpha using Symphony on the VLT, and also the dust continuum mission from ALMA. And we're finding that it's really important to go to these longer sub-millimeter wavelengths, because we think that star formation at kind of around the peak of cosmic star formation, redshift 2, is quite obscured and most visible at these long wavelengths. So one of the galaxies that we target turns out to be a very dusty galaxy. So even though we picked it out just by its H-alpha emission, which tend to be kind of average star-forming galaxies, this turns out to be quite extreme. So this is a galaxy at redshift 2. It's quite massive, around 10 to the 11 solar masses, forming stars at around 1,000 solar masses per year. So this is a particularly dusty galaxy. So it has around 5 millijansky flux at 860 micron, around 10 to the 9 solar masses of dust. So it's actually more like a typical sub-millimeter galaxy. So this slide shows our resolved imaging. In the top left, you have the rest frame UV continuum from HST in blue. Below that in green, the H-alpha emission. And then in orange, in the bottom right-hand corner, we have the dust continuum emission from ALMA. And this shows kind of different structures at the different wavelengths. So even though we often use both UV, H-alpha, and the dust continuum emission to infer something about star formation in a galaxy, these indicators show very different spatially resolved maps. So in particular, the H-alpha emission is quite extended, whereas the ALMA emission shows a more compact core. So the galaxy I've just showed is quite an extreme one from our H-alpha selected sample. But when you look at the literature, lots of other dusty galaxies show kind of similar patterns. So lots of galaxies show these mismatches in size and morphology, and often offsets between different indicators of light. So I've just shown here some galaxies from Jackie Hodge. So these are sub-millimeter galaxies. And she plots the ALMA emission shown in red. And this is much more compact than the extended rest frame optical emission, which is shown in green and blue. So it's quite clear that if you want to form a full picture of these high redshift galaxies, you need spatially resolved data at different wavelengths. And this is fairly expensive in terms of telescope time, and few galaxies actually have the full sets of data. And these kind of effects can be quite severe when you think about measuring star formation across the universe. So one example of this is the IRX beta relation. So this relates the UV spectral slope beta on the x-axis here to the ratio between the IR and the UV luminosity. So observers often use one of the lines plotted on here to convert beta, which is the observed spectral slope, to a total star formation via some inferred IR luminosity. But it's quite clear that the population of dusty star-forming galaxies doesn't actually fit very well on this relation. And one reason is geometrical effects. So if the majority of your UV light is coming from regions that aren't very dusty, you're going to underestimate the IR luminosity and hence the star formation rate. So I've been attempting to use simulations to kind of try and understand what's going on in these high redshift galaxies. And the aim of this work is to explore how simulated galaxies look at different wavelengths, and also to compare the emission to the other kind of intrinsic physical properties. So I've been using the Phi-2 zoom-in simulations because they resolve star formation on small scales and produce kind of fairly realistic looking galaxies. So if you're familiar with the main Phi-2 sample, the sample's a little different. We're using a sample of galaxies that reach Milky Way masses by redshift 2, because we want to match the simulations to the massive galaxies that are actually observable at these high redshifts. So we can take information about the gas and the star particles directly from the simulations, but we don't actually have predictions for observables. So to address this, I've been doing some post-processing, and I'm using the STScI radiator transfer code for this. So I supply to the code positions of the stars and the dust particles, assign some SED to the star particles, and then track how photons propagate through the dusty medium of the galaxy. And I place detectors at redshift 0, so I'm kind of measuring the simulated observable emission all the way across the wavelength spectrum. And I give STScI a number of different inclinations. So I want to study the impact of galaxy orientation as well on the measured emission. So this is just one example of if I put a snapshot into the post-processing, like what I get out. So this is the example SED. In black, I've shown the mean SED, so averaged over a number of detectors, and then in gray shows each detector's SED. And I've also overplotted some ALMA bands in color. So the one I'm going to use is the 870 micron band, which is shown in green. So if I run the radiator transfer on all the snapshots in the simulation, I can track this ALMA observable flux across redshift. So this is shown in the navy lines here. So I can see that the flux goes well above a millijansky for a substantial portion of the history of the galaxy. So these times, the galaxy would be sub-millimeter bright. And of course, there are many things I could do with this data set. So I could have plotted emission at any other wavelength. And I've kind of resolved this emission in time, as well as wavelength. And I can also resolve the emission spatially. So STScI outputs resolve maps of the emission. So this is just one example for the snapshot I show. So on the left, in black and white, I've plotted the intrinsic physical quantities output directly from the simulation. So things like the stellar mass, the cold gas mass, the dust mass, and the star formation rate, surface density. And in color, I've shown the results of the radiative transfer. So at the top, the rest frame UV emission in purple, going down to the far infrared emission in red. And you can see that the UV emission is quite clumpy. It's not really capturing the star formation in the galaxy fully, whereas the longer wavelength emission is more regular and disk-like, with a slightly kind of compact core. So the idea here is to use the simulated multi-wavelength maps to understand physical properties happening within the galaxies that we observe, and also the observational biases that affect how we see them. And one example is offsets between wavelengths of light. So I've just plotted here on the right the far infrared emission in red overlaid on the UV emission in purple. And you can see that if you observe this galaxy, you would kind of see some offset between the indicators. So one of the focuses of the paper we recently published was also looking at compact sizes of dust continuum emission observed at high redshifts. So So here I've plotted the effective radius of the dust emission versus the effective radius of the cool gas for the 5 galaxies in red, and I've overlaid some observational measurements in darker colors. And there are some kind of some uncertainties about this, but broadly we're reproducing the very compact sizes of dust continuum emissions, so a couple of kiloparsecs. So just to summarize, observed galaxies, higher redshift, show different morphologies when you observe them at different wavelengths. And to understand this, it's quite important to cast your simulations into observer space. So we've done this via radiative transfer. And identified a population of galaxies with some millimeter fluxes similar to what we observe, that also have quite compact dust emission and offsets between different wavelengths of light. So thank you very much. Yeah, so I mean, this is tricky in terms of observations. I think the current consensus is that the majority of sub-millimeter galaxies are not kind of dominated by an AGN. And you can tell that by kind of various things like far-infrared radio correlation, X-ray emission if you kind of have coverage. In terms of the simulations, they don't currently, we don't have AGN feedback implemented properly. So it's kind of consistent that without AGN feedback, you can reproduce compact sizes. One thing we're planning to do is kind of implement AGN feedback into the simulations and see what the difference would be. So see how the SEDs and the spatially resolved emission change when you have an AGN. Yeah, sure. Yeah, which one?
Next one. Yeah.
Yeah.
So, you know, the infrared image, kind of makes sense based on the physical thing that they're tracing.
Mm-hmm.
But the optical and UV, the regions that are bright in the gas and stellar moss aren't the same, and you noted that there is indeed an offset between the UV and infrared maps. So like physically, where is that coming from?
Yeah, so I mean, the idea is that physically you have dust in the galaxy, and the young light from stars is obscured by that dust and re-radiated at longer wavelengths. So in regions of the galaxy that have a lot of dust, you don't have as much short wavelength light escaping.
So you used a curve IMF. So my first question is, what is like the minimum mass of your star particles or cosmic particles?
So the minimum mass of the star particles is around 3 × 10⁴ solar masses.
Okay. I was wondering if you could speculate with the stochastic star emission, right? That means the star particles are so big. Curve IMF is what I find.
Okay.